Hello everyone and welcome to my new video series. In this video series, we are going to solve daily LeetCode problems. While solving these problems, I will do my best to explain my thought process behind this specific solution, and I will also try to focus on how would I approach this problem during an actual coding interview. Because there is a difference between actually solving a problem to make it accepted on the LeetCode, and the way I would approach the problem during the technical interview. And I will obviously give more examples uh, during this series. But like one example that comes to my mind is that during the technical interview, you don't have to make every little single detail work as long as your interviewer is okay with that. So for example, you need to write a helper class in Java, and you know that you need to implement equals and hashCode in it. So I think it's perfectly fine to just tell your interviewer that, okay, this time I'm not going to actually implement it. I will write some stub code and I will write in the comments that, okay, my equals is based on these fields and my hashCode is based on these fields, probably the same set of fields, but yeah. Okay, so let's move on to the actual problem. So today's problem has a hard difficulty, so which might indicate that it's not the best day for me to start this series, but let's see how it goes. Uh, okay, let's open the problem. So I'm genuinely seeing these problems for the very first time while recording this. So there might be some hiccups, but I think it's a good thing because this way you can see my genuine approach to solving these problems. Okay, so let's read the problem. We are given a grid, which is represented as an array of strings. And we have some empty cells, we have some walls, we have our starting point. We also have some keys and locks. Okay, and we are able to move in this grid, and we can move in 4 directions: left, right, up, or down. Okay, we are not allowed to step into the walls. We are not allowed to move out of the grid. And if we walk over a key, we can pick it up and and I cannot walk over a lock if I have a corresponding key. Interesting. So basically, yeah, we have this keys and we have these locks, and lowercase letter indicates keys, uppercase letter indicates locks. There are no more than 6 keys, but there is at least one key. Interesting. There is exactly one key for each lock and exactly one lock for each key. And okay. And our goal is to acquire all of the keys. And interesting. And we need to find the smallest amount of steps needed to do that. So immediately when I solve this type of problems, I think of graph problems, because this grid can be easily represented as a graph where each cell is a vertex of a graph and our transitions are vertices of the graph. So for example, from this cell that I'm pointing to between 2 walls, we obviously have 2 vertices. We can go either up or down. We are not allowed to go left or right because of the walls. So that's one thing that I immediately think so. But this graph, it's kind of a special graph because availability or not availability of certain cells is dependent on what keys do we have. So for example, we cannot go to this golden lock unless we also have a golden key. Luckily, there are not many keys. There are only 6 of them, which makes me think that we can kind of enhance the state of our graph. And previously we thought that, okay, we have a vertex of a graph is a cell in a grid, which is represented by the row number and column number, but actually we can enhance the state and also consider making a bit mask of what keys do we currently hold as a part of the vertex of the graph. So basically, I will write in the comments, our graph vertex is as the following properties: row, column, set of masks, set of keys that we have already captured. Okay, and this basically defines whether we can go to a certain cell or we don't. One thing that actually interests me, so suppose we have picked up a silver key and then we went through the silver lock. Does it mean that we do not like lose this key in this lock? So I think it means that since we acquired the key, we can go through the lock cell, the corresponding lock cell, any amount of time we want, because otherwise I think this won't be solvable in 8 steps. The example number 1, so let's see, what are these steps? So I go here, then I go here, here, I picked up the key on step 2, here, 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 so I moved in 5 directions, 6, 7, 8. Okay, so this neither proves nor disproves my hypothesis. But let's maybe read the statement one more time. Yeah, it doesn't say anything that we lose the key when we move through the lock, so I think it's fine. And yeah, in this example, the shortest amount of steps is 6, because here we go here, then we pick up the key, then we have the corresponding key, so we can go here, and then we go down and we pick up the golden key. And yeah, in example 3, we cannot possibly gather all of the keys because we need to pass through the lock, and we cannot do it without the key. So unfortunately, yeah, the answer is -1, which is fine. Okay, so we are also guaranteed that I think they said at some point that only the first K letters of the alphabet will be used. Let's see. Okay, lowercase letter represents the key, uppercase letter represents the lock. For some K, there is exactly 1 lowercase and 1 uppercase letter of the first K letters of the English alphabet. So yeah, this helps us a little bit to make it easier. So what's the idea of the solution? We have this graph where each vertex is represented by this set of properties, row, column, and a set of keys that we've already captured. And this set of keys is very convenient to store in a so-called bit mask, which is basically an integer, which we consider that, okay, we have it in binary form. And if the bit is set to 1, this means that we have the following key. And if it's set to 0, then we do not have the following key. And it's kind of easy to check with some bit operations like shifts and ANDs and so on. So bitwise AND. I will show it how it works a little bit later. Okay. So yeah, this problem is definitely not going to be easy to implement. But the general idea is, since we have this graph and we can transitions. So suppose we are standing in a vertex, which is represented by some row, some column, and some set of keys. We will try to go to all of the neighboring cells, and we will take a look at them. If they are outside of the grid, then we are definitely cannot go there. If the neighboring cell is a wall, we can definitely not go there. If a neighboring cell is an empty cell, we can obviously go there. If the neighboring cell is a key cell, we can go there, and we potentially might add this key to a cell if we have not already acquired it. And if the neighboring cell is a log cell, then we will take a look at our set of captured keys, and we will try to find if we have already acquired the corresponding key. So if we do, then we can go there, and if we don't, we can't. And obviously, this graph has the edges of weight of only 1, which means, and we want to find a shortest distance in this graph between our initial state of start row, start column, and 0 mask, which means no keys. And we want to, our initial state equals to this, and our final state equals to any row, any column, and full mask, which means that we acquired all of the keys. And if we have exactly k keys, the full mask is actually equal to 2 to the power of k minus 1, which is kind of easy to see. So for example, k is equal to 3, and we have 3 bits set to 1. You can see that it's equal to 7 in decimal, which is 2 to the power of 3 minus 1. And yeah, it works for every k. Okay, so let's try to write a solution to this problem. So first of all, I will try to make this as readable as possible. And this is actually what I would do at the actual interview. So our first goal, quite an easy one, is to find our initial square, which is represented by this @ sign. So let's find it. Okay, so I guess we will need an helper class, which is very easy, but we will call it coordinate. We can make private static class actually. And it will have 2 fields, only let's call it row and column just to make it 100% clear. And let's write, we can actually make it even private final, because it's always a good idea to make your class as close to immutable as possible. And obviously we will have a public constructor. Okay. And we are also going to have some public getters. Another thing that I like to do while solving problems at LeetCode is writing some code, even non-functioning one, and then just run it to see that it still compiles, which might not actually be the case. So in this case, it compiles, but obviously we are returning the wrong answer because we didn't implement anything yet, and we are returning 0 all the time. Okay, so as I said before, now let's write a method that will find the starting position of our character. Okay, coordinate, which is nice. We have this class now. Find initial position, and we will pass a grid to it. Okay, so let's iterate over our grid. Yeah, that's right. And here length is a method, probably. I'm not sure. But yeah, we will see slightly later. So, and if read I char at j is equal to this head character, and we will just return new coordinate. Awesome. Otherwise, we will return null, which should never happen. And actually, it's a good idea to ask this during the interview. Is such a corner case possible or not? So this problem always guarantees us that it's present. So this statement will hopefully never be executed. But yeah, it's always good to know. So let's call this method. I always like to copy such one methods, and we'll pass grid here. And once again, let's run our code. It still compiles. Awesome. Okay, so now we know our initial position, which is this coordinate and mask of zeros. So then we can write our transitions. I think we will need an extra class for that, which is, let's call it state for now, and it will hold our coordinates, and it will hold our mask. Okay. So we have this state, and it would be good to actually, yeah, we need to appoint a public constructor, obviously. Okay, let's do it. It would be so much easier to implement this in IDE. I'm thinking, should we maybe not have a mask, but just have a set of available keys? I don't see a reason why not, to be honest, at this stage. So let's maybe not commit to a premature optimizations and just have a set of integer, which we will call keys. And I think it might help us later on. And then we'll expect this keys equal to keys. And let's compile our code. So it still compiles. Awesome. Okay, so I would also suggest in this, so that in this state class, we will also implement our transitions. So how do we do this? For a given state, we want to know what next states are possible from this one. So let's do it. Our method will, let's call it, it will be public method. It will return list of states, and we'll call it next states. And it will consume our grid as an argument. And yeah, we will probably need an extra helper method. We will call it private state next state. It will have a grid. It will have, and it will also have two variables which will indicate where are we moving. So we will call them delta row and delta column. And you will see how I'm going to use this method later on. So let's implement this method first. So first of all, let's see. And our idea is that if the move is possible, we will return a corresponding state. And if it's not possible, we will return null. And then we will call this next state method 4 times here. And we will filter all of the nulls. And then we will just return it. So the code speaks better than the words. So let's see. I'm going to do this. I'm going to do return string of next state of grid and delta row now delta column -1, which represents a move to the left. Then next state grid 0, 1, which represents a move to the right. 1, 0, which represents move down. And one more call, which represents move up. Okay, then I will filter this stream based on the object not being equal to null. So which can also be probably improved via some method references, like objects not null or something, but I don't remember the exact syntax. So yeah. So we did that, and let's collect. And let's hope that this works. And for now, let's only return null here. And let's run our code to see if it still compiles. It does. Cool. So let's implement next state method right now. Okay, so let's see. Our next row is equal to coordinate get row plus delta row. Our next column is equal to coordinate that column, delta column, is nice. Okay. So first order of business, let's check if the cell with coordinates next row and next column belongs to the grid. So let's do this. And we will have a separate helper method for that. Private boolean inside grid. Okay, let's check it. So we need return true if and only if row is greater than or equal to 0 and column is greater or equal to 0 and row is less than grid length and column it's less than grid row length. Okay, and then we can check if we are not inside the grid. Then we can just return no because this transition is not possible. Let's run our code to see if it still compiles. It doesn't. Interesting. So it doesn't know what's row and column because our variables are called next. Oops. Yeah, because our variables are called next row and next column. Awesome. So we found this error early, and one of the key principles of ours is let's try to find every error as early as possible because it's much easier to fix them now. Now we have a compiling code, which is good. Okay, then let's get our character. It's equal to grid next row, next column, and if next char is equal to the whole character, we can return no. Because it means we can never go to the wall. Cool. Okay. If next char is an empty cell, we can actually return a new state. And our first argument for the constructor is coordinate. New coordinate, next row, next column. And our set doesn't change. So we will just create a new hashset from our current state of keys. And that's it. Okay, so let's see if it works. It still compiles. Awesome. Suppose our next character is actually a letter of a lowercase English letter. So let's check for that. If it can be a separate check, I guess. But yeah, we can definitely have a method here. And I think it's worthy to mention it during the actual interview that I would refactor this if to a separate method. But I'm not going to do it now. So what this means is that we have a new key, and let's call it next key, and its number is equal to next char. Actually, we can just keep a set of chars, but okay, let's keep a set of integers. And then we can say that set of integer next keys is equal to new hash set keys, but we will also add a next key to it, and then we will return new state of this and next keys. So let's run our code. It still works. So the only part that we have not considered yet is a log. So let's check it out. Okay, so let's see if we have a needed key. Our needed key is equal to next char minus big letter A. And if our keys contains this needed key, then we can go there. Otherwise, we can't. So if we can go there, then we can just return this state. And if we can't, we should just return now. Actually, we can even get rid of it because it will be returned here. So let's run our code. It still compiles. Awesome. So let's go back to our initial implementation. Now we have these transitions, which are very nice, as you will be able to see very shortly. So let's implement our breadth first search, as I said before. To do that, let's keep track of map state integer distances equals new hash set. And let's hope that default hashCode implementation is good enough for us. And if it's not, we can always deal with it later. But that's something that I would mention during the interview as well. And let's put our initial state through this hash map. Okay, let's create it first. Initial state, new state of initial coordinate. Let's go with initial position or something. And empty hash set of keys because we don't have any keys just now. So we can put in our distances map a value of initial state, and we can get there in 0 steps, which is cool. And we should also have our queue. There is a default, there is some interface for queue in Java, but I'll be honest with you, I don't remember how to properly work with it. So we can either Google or write our own queue. So we can do both, but for now let's go because I think it's better just to see the Java doc of Q. Okay, so here it is. And let's see what implementations do we have. Okay. So whatever, we can choose, I don't know, linked list. And here are our methods, which is good. Okay, so let's go by this. So we have Q. State. And let's just create a linked list for that. I think it's fine. And we will add an initial state to this Q. Let's see if our code still compiles. It doesn't. Interesting. Oh, sorry. Yeah, I messed up. Of course, we need a hash map here. So yeah, very easy mistake. Okay, now it compiles. Good. And one thing that I actually thought of just now is that it's important for us to know how many keys are there in general. So because otherwise we won't know if we have reached our final state. So let's write a short method that calculates it. Number of keys. So once again, we will iterate through our grid and we will take a look if this character is a lowercase character. And we will just implement our result and we will return it. So yeah, it's important to know it. Let's see if our code still compiles. It does. Awesome. Okay, now let's write our breadth cursor, which should be pretty trivial at this stage. So while our view is not empty, we should poll our state. Okay, so the method is called poll. Cool. State current state equals then we need to take a look if the state represents one of our final states. And to do that, we will need to implement a new method in the state class, which is called public int number of keys. And it will simply return keys size. Cool. So let's see if current state number of keys is equal to the total number of keys, then we should just return the distance of state. Okay, our code should still be compiling, but it's not. Because yeah, it's not C++, so you cannot write it. You should write it like this. Sorry, I'm a little bit tired already, which is kind of funny. Okay, let's see. It still compiles. Awesome. Okay. So if it's the final state, then we know what to do. Then let's find all of the possible next states. Current state, and let's go next states of grid. Interesting. Oh. So let's iterate over this possible state. Okay, and let's also have our current distance variable, which is equal to distances gap current state. And here we can just return current distance. So here we will take a look. If our distances map contains key of our current next state, then according to breadth search algorithm, we shouldn't do anything. So we can just move on. And otherwise, we will just put this next state to the map and to our queue. So we write, so the distance became bigger by 1, so our new distance is current distance plus 1, because we made one step. And we will also, okay, what's the interface? We will add our map state. Fantastic. And if our breadth search haven't found anything, then we are supposed to return -1, as is indicated here. So let's run our code, and maybe, just maybe, it works. Okay, so at least all of the sample tests are passed. Let's submit it. Okay, so we've got time limit exceeded on white and easy test, which is interesting, I would say. And now the debugging will begin. Oh yeah, this might take a while, but let's hope that it don't. So we will use this test case. Obviously, that's a pretty nice feature of LeetCode, so that we don't have to submit every single time. We can just run it. So let's see what's so special about this test case. Let's maybe visualize it. I guess since the input is so small, we never actually leave this loop, which is not great. But yeah, let's see. Well, this is our example. And this is our initial position. And yeah, we start here. and then I see. So yeah, it's possible to collect all of the keys, I think. For example, I'm not saying it's the shortest path, but we can go all the way down. Now we can go all the way up. Then, so yeah, we've collected the B key. We went all the way up. We've collected the A key. We moved all the way down, and we've collected the C key. So yeah, it's interesting. Let's maybe write some debug output, but I'm not sure what can it be. Let's maybe examine the code a little bit. Or let's, I don't know. I'm not sure what's very helpful at this stage, except of looking through the code, which I will do right now. So we're finding an initial position. Okay, does qpol actually remove something? I hope so. It should. It should. We can always check. But yeah, as I said, it's probably a waste of time. Yeah, it definitely works. Okay, at some stage it grows really fast and then it goes back to. Aha. Okay, probably it shows the output for everything, which is not very good. Okay, so poll definitely works. Okay, yeah. Let's look through the code. Yeah, I think that we will need to implement equals and hashCode for our next state, or otherwise it will not work, right? Let's think about it. Yeah, absolutely, we need to do that. Or do we? Yeah, I think we need to do it. Okay, so let's do it. And let's, okay, let's take a look. If other equals this, then we can return true. Then we should return false. And yeah, during the interview, I would say that, okay, I would just implement it and it should work. But fortunately, that's not what we can do on LeetCode. So yeah, let's implement it. Okay, so this will be our first equals. Let's run just to see if it still compiles. It doesn't. Okay, I will need an extra set of brackets here. Paper over here. Okay. So now let's override hashCode. We will simply return some hashCode. I don't know, 31 times row plus 1, something like that. Okay, let's run our code. Still works. Okay, now let's do the same for this state class. And yeah, we will do basically the same. So if other is equal to this, we will return true. If other is not instance of state, now return false. And then we will return what we will return. We will return or all this is called coordinate equal and is equals okay. Let's see if it still compiles. It doesn't. Because yeah, it's other state. It compiles. Now let's override hashCode. Times coordinate hashCode plus is hashCode or something like that. Okay, as you can see, I'm already slightly tired, so making this mistakes, but yeah, it still works on the samples. Let's run it on all of the tests. And now it produces wrong answer. So it no longer produces time limit exceeded, which is great. And we actually passed almost all of the test cases, but now this test is failing. which is quite bad, I would say. So this is our grid. Is it the same grid? I think it might be the same grid. Yeah, I think it's the same grid, which is not great. Yeah, sorry about that. I had to step away for a second, but now I'm back and we still have the same problem. So let's probably take a look at it. Our solution is pretty massive already. But the good side is that it's relatively written in an understandable way. So we can, I don't know, write some debug output. And to do that, we will probably need to implement a string as well in here. So let's do this. Public string. And here we will just return okay, let's see what it does. Okay. And now we're going to implement a string over here. Okay, then I will probably just write it like this or something. Okay, now just let's debug output every single state that we are in. Okay, so, and our case is here. So let's maybe make it like this so that we can look at the grid and at the debug output. Maybe copy it. Oh, it didn't copy it. That's not great. Let's run out. Okay. Our test case number 4 disappeared, so we will need to do that. And yeah, let's copy it. Yeah, that's it. Interesting. So initially we are at the state 0, 0 with an empty set of keys. And yeah, 1, 0 with an empty set of keys. Yeah, from 2, 0 we can go to a set of keys which is equal to 1. And from there, yeah, we can go to 1, 0 with of 1, which is good. Then, I've seen my error. Okay. In our next state method, we should also be able to go back to our initial position. So here it's very easy fix. We can just do this. So we can always go back to our initial position. It is allowed. So yeah, let's submit our solution. It's started to perform less. Oh, I'm an idiot. Because here it's obviously or. Sorry about that. I'm really, really tired. Let's hope that it passes this right. Yes, it finally passed all of the tests. So yeah, very interesting problem and not trivial at all. But yeah, I'm glad that in the end we made it work. Kind of had a couple of hiccups on the way, especially the one with equals and hashCode, which is kind of intuitive if you think about it. But yeah, so it's very interesting. I will post my solution in the comments of this YouTube video. So yeah, if you want to see such solutions in the future, please like and subscribe. And this problem was a hard one, so the video is kind of a long one, but it's one of the hardest problems that I've ever solved on LeetCode in terms of code complexity, because the idea is pretty straightforward, but you need to write a lot of boilerplate code, especially in Java, to make it work and to make it look reasonably good. So yeah, hope to see you again on my next video, and feel free to post any comments that you'd like. Thank you very much. Bye-bye.